All right, good morning, everybody. So I did see a message that you guys could hear and see everything okay. So what we're going to be talking about is Modbus Basics. So you may have heard Modbus, the protocol. We're going to go through the basics, kind of historically where Modbus falls, how LS utilizes Modbus with their various products. We'll be doing a live example. We're going to be giving a breakdown of how the numbering scheme and the words and the bits and everything works. So this probably won't be too long, maybe 30 minutes or so. Everybody is muted currently. At the end, I think you could raise your hand. You could type in a question. I think we could unmute you and stuff. Also, we are going to record this and we're going to put it on our YouTube either later today or tomorrow. So if there's anybody you think that would benefit from this, you could always share it with them if they missed out today. So here's what we're going to go through in order. We're going to go through Modbus Basics, just kind of what is Modbus, why people utilize it for their application. We'll spend a lot of time on VFD setup. This is what we get questions on multiple times a day. Modbus is the most popular protocol, so we get a lot of questions about mapping the Modbus registers, programming the drive. How do we wire it up? How do we troubleshoot? We'll have a little troubleshooting section in there as well. And then what I'm going to do is I'm going to show an HMI that is actually pre-programmed to work with the VFD. So after you understand the programming, the wiring, the registers, you'll kind of see how it all works together. So we'll end with a live demo. So what is Modbus? Modbus is a serial communications protocol, and it's actually been developed in the late 70s, 1979, by Modicon. It's open source and it's royalty free, so therefore it's commonly used. You don't need to pay to use the protocol. So, you know, whenever you don't need to pay for stuff, it tends to be popular. So it's actually one of the more popular protocols in industrial applications. Additionally, you should note that there's two different transport layers possible. There's RTU, which is remote terminal unit, and then there's TCP/IP. So that changes the medium in which you're connecting to. So in our drive, I'll show you S+, S-, two-wired twisted pair. That's RTU. It's a 485 connection, whereas TCP/IP is, as you'd guess, it's an IP-based, so there's an Ethernet cable. Modbus is a client-server, master-slave protocol. So this means that the client or the controller actually needs to pull the data from the server. So if you ever get involved with making a PLC program, you need to pull the device. So in our case, a lot of times you're setting up a ladder logic that's going to pull one drive or multiple drives over the network. We can't just read all the data at once. We need to do it in a sequential order. Additionally, some things to note, the network is limited to one client. So that's one master. And then you could have up to 247 servers, so 247 slave devices, but you're actually only limited to 32 servers if you do not have any repeaters. Most of the time, people don't run more than 16 or 32 devices. Modbus is not the fastest network, so you are kind of limited in that. So if you have any kind of high-speed, precise application where you need data fast, usually you're not going to use Modbus because it's kind of more basic and a little bit slower. So you can actually see on the bottom here, I have this little picture. The PLC is your client, VFD is your server. So the PLC says, does the polling operation. It's going to say, hey, what's your speed? Then the VFD will reply, I'm running 60 hertz, for example. So that's the polling operation. Data structure and size. This is another common question we get every day is, what's the VFD giving me? So we'll get a call from a controls engineer. He says, what's the drive giving me? Pretty much the VFD for LS uses holding registers. So we're looking at the bottom two rows on this table here. But there's actually a lot of things you could run into. There's coils and contacts. Those are just 1 bit. So that's like an on or off bit, coils and contacts. And then there's registers that are 2 bytes, which is 16 bits, and that's actually called a word. So we get that question a lot. It's kind of like a jargon term that's thrown around a lot is a word. So what's the word I need to read? It's a 16-bit device, and within that device, that's 2 bytes. There's the 16 bits. Okay, so we're going to break it down a little bit further later on in these slides. So long story short is when we're talking about all these registers, is a register is simply a location to store and look up data. So everything in Modbus is stored in registers, and what Modbus is doing is it's reading and writing data. Okay, so it's data acquisition is what we're doing here. So if you look at this table on the bottom right here, first see that there is different types. There's read-write types, there's read-only types. Okay, so those are the two types. So if you try writing to a read-only register, you may get an error, you may get nothing back. So just be aware of that. And so here we're showing you all the possible list of registers, so all the way up to 49,999. Okay. Another important thing to note is the addressing. So addressing must be unique. So let's say we have 3 VFDs on a network. The first drive would be drive number 1, second would be 2, and actually I have a typo here. So that's what you don't want. It should say number 3 on the far right. If you had 2 drives set up for 2, you're going to get collisions, you're going to get some mismatched data back. So if you say, if the PLC, again, is running the polling and it's saying, all right, number 1, what's your speed? Number 1 is going to be the only one to reply. Number 2, number 3 says nobody's talking to me. So they actually, if you were to look at the message going out to the clients, or from the client to the servers, the first byte in the message is actually going to be the address. So it's going to say address 1, address 2, address 3. So you need a unique address on each VFD. Also, another common thing that we need to explain to people, or refer them to some kind of guide, is going to be the numbering scheme for Modbus. So first off, Modbus works with a bunch of zeros and ones. So it's binary. So there's low voltage pulses across the communication line. So on is 1, off is 0. Voltage on, voltage off. Okay, so we're sending a long string of numbers. So the rate at which these zeros and ones are sent, so those are bits, are the baud rate. So if you ever hear 9600 BPS, some 11.5, 19.2, that's bit per second. That's your baud rate. So that's important to be aware of. And also your baud rate needs to match up for every device on the network. Also, be aware of the register addressing. So if you're looking at a Modbus map, some devices will be in decimal, some devices will be in hex. So you got to do some conversions there just to make sure you're all on the same page. So we'll mention later, LS devices, we list everything in hexadecimal. Also, this is maybe the biggest trick, is that there's oftentimes an offset. So things are decremented by 1. So if you want to look at register 6, sometimes you'll actually find there's a decremented offset. So you actually need to do register 5, a read or a write. Okay. On the right here, you could see the decimal, so base 10 to base 16 conversion. So 0 to 9 is all the same, but once you hit 10, 10 doesn't exist in hexadecimal, so it actually goes A, B, C, D, E, and then F. So that's from 0 to 15, 0 to F, decimal over to hexadecimal. Also, I'll show you, you could just use the Windows calculator, and that'll convert decimal to hexadecimal, hexadecimal to decimal, and you could even go to base 2 binary. Wiring is pretty simple. So it's, first off, Modbus RTU is standard on all LS VFDs. Even the M100, our most entry-level drive, has built-in Modbus RTU. Also, for most of the drives, we have a Modbus TCP IP card you could get. So that's a field-installed accessory, just snaps into the front of the drive or maybe slides in with a couple of screws depending on which series drive you're looking at. Of course, we recommend following all recommended wiring practices, which I'll mention in a second. So if you follow the guidelines and the proper wiring, then it's going to save you a lot of time, a lot of headaches. Anybody that's worked with Modbus knows that communications either works or it doesn't, and when it doesn't work, it could be quite the headache. Even harder than that is troubleshooting noise issues where communications is randomly dropping out. So these bullet points on the bottom here is we're mentioning some of the key specs and recommendations to follow. So Modbus RTU uses a daisy chain line topology. So you're pretty much just jumping one drive to another, S plus to S plus, S minus to S minus, and then doing it again and again and again down the line. We recommend that the signal cable is a twisted pair, and we also recommend that you have it separate from your power wiring. So try not to put your low voltage communication cable in the same conduit as your motor or your incoming power and stuff. Try to keep that separate. We recommend a 22 gauge minimum. You could also use larger gauge if you're going across longer distances to compensate for the voltage drop. Shielded cable is also highly recommended. You only need to land that shield on one side of the devices, so typically you'll have it on your host controller. And then also all of the VFDs have a built-in termination resistor. So that terminating resistor should be on the last device. So if you have 5 drives, you flip the switch on. So it's going to be like SW2 or something like that on the drives. You could always check that in the manual. And then I'll also show you guys, we do have a master Modbus reference guide, which actually shows how to connect, how to program all of the VFDs. Another thing to note is if you look on the right here, this picture, so the M100 and G100 are micro drives. You actually have 2 different connection points. You could pick and choose what you want to do. We have screw down terminals, S plus, S minus, or it's kind of nice, you could actually plug into the keypad port. So a little RJ45 jack, and the 2 outer pins there are your plus and minus going to the network. So that's a little bit easier because it's just plug it in instead of screwing anything down. So that's an option. So some other things to note, in particular with Modbus and how we do it here at LS Electric is, and I mentioned this a minute ago, registers are listed in hexadecimal. So, I mean, you could just look on this table on the right here and you start seeing F's and D's and E's and stuff. Obviously, that's not decimal numerals. It's going into hexadecimal. So the user manuals and all of our reference guides list everything in hexadecimal. So you could use a Windows calculator, or you could just, Google conversion, just like you would convert metric to imperial units and stuff like that. And you could convert, the different, decimal to hex and vice versa if you need to. So on the right here, this is actually the full memory map. So if you went to the table of functions in any of our manuals for a VFD, all of the parameter groups are mapped to Modbus registers. So you could actually change all of your parameters over Modbus if you wanted to. So there's certain parameters when people are writing a program that they change a parameter in the VFD. So that's all found on the memory map in the user manual. All right, so let's look at the actual registers for Modbus. So all of the LS VFDs have a list of what we call common registers. And these common registers are common across all the VFD series. So H100 plus, S100, IS7, etc. So for example, if you look on the right here, your frequency command is register 5. That's hexadecimal, but we're less than 10, so it's just 5. Okay, there's nothing to convert there. 5 in hex is the same as 5 in decimal. So this is a read-write register. So it says R/W here. So if I was to write a 6000 here, it would go to 60 hertz because there's 2 decimal places here. And this would be the same register on an S100, an H100 plus, an IS7, an H100, a G100, and so on. So if you're communicating with multiple LS drives, it's all the same register. So it makes it a little bit easier from the programming side, from your controller, PLC, or HMI, or whatever you're using. So also, this list, I don't know how many there is on this list, but maybe 30 or so. These are also very commonly used registers. So your run command, your frequency, you could run reverse, you could run forward. If you look at the bottom of the list, you got your XL time, your decel time, your output current, frequency, voltage, DC bus voltage, power, things that you want to monitor. So a lot of the common things that people are reading and writing to are on this list. Okay? And also be aware that there is that RW column. Some of these registers are read-only, some are read or write. Okay, so again, if you try writing to a read-only register, it's not going to work. All right, parameter setup. So this is actually a little snippet out of our Modbus master reference guide. So key parameters that you need to set on the VFD are going to be baud rate. So that's CM or COM3, depending on your keypad. We always default to 9600 BPS. Other things you got to worry about are the parity, the stop bits, and then the data size. So if you look on this table, CM04, we always have a data size of 8 data bits. We have a parity that defaults to no parity. If you went to PN, that's no parity. PE is even parity. PO is odd parity. And then you could actually select the stop bits. You could select 1 stop bit or 2 bits. So if you look right here, we got option 0, 1, 2, and 3, and you could customize that. These parameters need to match the host controller. So if you're running a 9600 baud rate from your controller, the drive and any other devices needs to be 9600. And your data size, your parity, and your stop bits also need to match as well. Once in a blue moon, we do adjust COM 5. This is your transmission delay. So, I mean, it's not much of a delay at all. It's 5 milliseconds, so it's going to respond pretty fast. So this is how fast it takes to respond to a message. Sometimes if you get a lot of drives on the network, you might want to stagger this out and adjust this a little bit. So you're giving the drive more time to reply pretty much, a little bit more of a delay. And then the last one we'll mention is DRV and FRQ. This is the same as DRV6 and DRV7 on the bigger drives that give you the LCD keypad. So if you're going to be running over communications, and if you're going to be changing your speed over communications, you got to go to the command source and your frequency source, and you have to set it to 485. Okay. If you had a Modbus TCP card, you'd actually be setting it to a field bus. That's saying, hey, look at the field bus option card I installed. All right, so after you're done with your programming, it's a good practice to cycle power. I've done this before where I set up a bunch of network comm stuff and I don't cycle power and I spend 2 hours trying to get things to work, and all I really need to do is cycle power and it works right away. So after you do any initial setup for programming, especially related to communications, it's good practice to cycle power. And also what I recommend is I recommend reading a register that has a live value. So sometimes people are like, all right, I'm ready to run. I want to give the driver run command. And they try to run and nothing happens. Then they give us a call. And I say, all right, well, let's figure out if you have an offset or not. So if you want to figure out if you have an offset or not, let's pick out a read-only value that's going to have something like DC bus voltage is what I usually start out with. So you should be at 320 volts for a 230 volt drive. So find the DC bus voltage register, read it back and see what you get. If you get back nothing, try the offset, go down 1, and then you should get something. So then you kind of know you're placing and everything is offset by 1, and then you could just start reading. So don't try reading a register that has a value of 0. So for example, if you're stopped and you're going to read output frequency, you're going to get 0. So it doesn't really tell you much because many registers could be 0, especially when you're stopped. So try reading a register that's like a live value that you know is something greater than 0. Some other tips is after you get the read and you get everything situated on if you have an offset or not, you kind of find your place, then you could try writing. Okay, and I do have some examples. I'll show you reading first and then writing. It's also recommended if you have any issues, sometimes guys like to just start, using their, Rockwell PLC or whatever PLC they're using, and they have all this code running. But there could be some things that are interfering with the communications. So sometimes I'll just say, hey, step back. Let's use like a free third-party communication software and let's just try a read. Can we connect to the drive? Are we able to read data? If you're good, then okay, the drive's okay. If it's not good, then you probably got to go back and check those 3 or 4 parameters that we mentioned earlier. Okay. Additionally, for Modbus TCP, so that's the IP-based one, I recommend pinging the device. Make sure you can connect. So if you're not getting any data back, let's see, is the drive even on the network? You should be able to bring up a command prompt in Windows, set up your laptop to the same network, and ping it. If you can ping it, that's a big step forward. If you can't ping it, you might need to revisit your programming. Usually it's like a bad IP address or something. Same thing for Modbus RTU. It doesn't use IP addresses, but it does use a node address. So COM or CM01 is the unique node address. So all the drives default to 1, but only one drive on the network could be set to 1. So you got to set in ascending order, 1, 2, 3, 4, and that has to be a unique address. Otherwise, you're going to have communication issues. So here's an example of a third-party program. So I like to use this BaseBlock Comtest Pro. It's free. You could download it off of their website. And in this example, we're going to read register C. And our C, if you look on the bottom left table here, that's your DC link voltage. It's a read-only register, and it's going to show you your DC bus voltage on the DC bus capacitors. But we actually found out that there's an offset. So if I read C, I'm actually going to get back a 0, okay? And then, but it should be a 320 volts DC, kind of as I mentioned a minute ago. So if you go down to a B, then it's going to come up with the 320 volt DC. So that's showing you right here where it says read registers. So now we know there's an offset of 1. So if I start writing, that offset's still going to apply. Okay, so again, start with a read. So then you can move on to writing. So in this case, I'm writing to register 5. Okay, so register 5 is actually register 6 on the Modbus map, but there's a decremented offset. So we go down from 6 to a 5. Okay. And you can see this register actually is using bits. So bit 0 is a stop, bit 1 is forward, bit 2 is reverse, bit 3 resets a trip. You could do an emergency stop and so on. Okay, so if we turn on bit 2, so that equates to a 4. Okay, so it's binary. So bit 0 is a 1, bit 1 would be a 2, and then bit 2 would be a 4. So if you remember binary, otherwise you could always use the calculator. So when we send this register 5 a 4, the drive's going to run in reverse. Okay, just like you're running off of terminals, you can't run forward and reverse at the same time. It's got to be one bit or the other. So explaining the bits a little bit further, as we mentioned, the LS drives use holding registers. So this is actually a 16-bit register. So there's a lot of data in there. So some registers are just a numeric value. So like we read the DC bus voltage, it gave us 320 volts DC, whereas other devices are going to contain all those 16 individual bits. And actually what it does is it adds the bits up. So in this example here, we're reading register 5, which equates to register 6 because of the offset. And I was in this example, I was reading back a 66, so 66 decimal, and hopefully you can see it on the bottom. It might be a little bit cut off, but I used the Windows calculator. I put in 66 decimal. I went to the programmer mode, and then it gives me the binary value. So it's 0, 1, 0, 0, 0, 0, 1, 0. Okay, so we could look at our table here, and we could see that this simply means that the drive is running off of the keypad, and then it's running a forward operation. Okay, so that 66 equates to a forward run off of the keypad. Okay, so you may need to do that. If you're good with PLCs, as you know, there's like unpacking and repacking bit operations that you could use, and it'll actually do all this work for you. That's the benefit of PLC. It's just a computer that's helping you out. Okay, so we're getting close to the live demo example I have set up here. So we mentioned a lot about VFDs and PLCs and controllers and stuff like that. So an HMI is essentially a controller. So an LS does sell HMIs. So you could actually customize the HMI to match a given network. So we have a long list of drivers. There's probably 100 different drivers. If you open up the HMI catalog, you'll find it there. In this example, I'm going to be doing a Modbus RTU driver because that's what this webinar is about. So you could actually set up the HMI to be either a client or a server. So it could be a master or a slave on the network. Also, the HMI is going to have the exact same settings as a PLC or a VFD. It's going to have a baud rate. It's going to have parity, even or odd, or none. It's going to have stop bits that you could adjust. And then it's also going to have a unique address. Okay, so that address needs to be unique. The VFD needs to be unique. Everything needs its own address. And everything needs to match. Okay, so your VFD needs to match your HMI, just like it would need to match your PLC. The more devices on the network, more setup you got to do. Just got to make sure everything matches except for that address. Address needs to be unique. So the HMI includes a bunch of objects, and what objects are buttons, displays, numeric inputs, numeric outputs, animations, switches, all kinds of stuff. So I have a pre-written program that we made here, and I'll show you, hopefully to kind of understand all the stuff we've been talking about. You'll see how it all works together. These are actually mapped to match the device's corresponding registers. Okay, so I'm going to show you the program, and I think it'll all make sense. So let's see it work together. So I'm going to jump back into this troubleshooting section, but first I'm going to show you guys the HMI program here. Okay, so this is a pre-written program. This is a sample program. It should be on our solution square. If not, you could always email us about it. I think a lot of people have my email, or you could email us at the tech support email I'll show you at the end of this session. So on the top left here, under the project settings, there's XGT panel settings. I'm going to double click that. And here's your driver, okay? So here's our HMI. This is an EXP2 series HMI, 7-inch screen, and we're running a Modbus connection, 485. We're using serial port COM3. And if I click detailed settings, this is exactly what you're talking about, right? Baud rate is 9600, data bit is 8, we have one stop bit, no parity. So you would actually go over to the VFD, you would check your COM parameter 1, 2, 3, 4, 5, I think it went up to, and make sure that that matches the same settings as here, okay? So this needs to match. If I go ahead and change the baud rate and it doesn't match the VFD, you're gonna get lost communications, it's not gonna work. So I test this ahead of time just to make sure there's no hiccups, and this does match the VFD settings, okay? So I'm going to hit OK here. And so these are all the objects we're talking about. So right here, if I double click this run button, this green button, this is saying that it's actually writing to address 1. That's what this #1 means. So the drive is node address 1. We're actually writing to register 6, and we're sending a value of 2. Okay. So I've been alluding to this Modbus master reference. So this is available on our knowledge base, the solution square, our website. It should be pretty much everywhere. So here is the master reference. So it starts out with a table of contents, and then you're going to have common registers. Okay, and then you're going to have common parameters for Modbus setup for each series drive, and then you're also going to have the wiring. Okay, so my setup here is an H100 plus, okay? So the wiring is, let's see, I think it's one more over. So H100 plus is the same wiring, okay? So here's that termination resistor, SW1, that should be on the drive since it's the last device on the network. I just have a small network of 2 devices here. This is showing daisy chain, S plus to S plus, S minus to S minus, so wiring is easy. Here's the parameters. So we're running a default of 9600 BPS. We have a default node address of 1. And then I also changed DRV 6 and 7 to run over the Modbus. And that's really all we need. Okay. So if we go back to the common registers here, and if we compare this register list to this HMI program, so we're actually going to register 6, and we can actually tell if there's an offset here. Okay, yeah, so register 6, there's no offset. This Excel sheet here has with offset and without, so we don't have an offset. We're giving it a forward operation, so we're turning on bit 1, that equates to a 2 in decimal, okay? So, right, we're sending it a 2, that's a run, that's a start. If we send it a value of 3 to the same register, that's a stop, okay? And then this one is your speed reference. This is register 5. I'll show you guys that. Register 5 is your command frequency. So that's an input. So see how it says read or write. So we could do either or. And then the last thing I show you before I flip this on is, so those are all actually word devices we're using there. So even though we're like turning on a bit, we're doing it through a word switch. So that's what the device is called, a word switch. This is actually a numeric input. So on the top, it's a numeric input. And then these right here, these LEDs, these are actually bits. So this is register E is an echo, and see how it says bit lamp. So we're monitoring bit 1. So if we go back to that table and we go down until we get to E, actually it should be, let's see right here. So 14, so this table is actually showing it in decimal. So 14 would be E in hexadecimal. And we could see the bits right here. So we could see a fault trip and then we could see for running forward or running reverse. So if either bit 1 or 2 comes on, that's a run condition. So this would be 2, this would be 4, this would be bit 3. So we could go back to our program here. So let's go look at like a fault trip. That should be bit 3, right? Yep. Register E, bit 3, when the drive trips out, that's going to go on. Okay. So what we could do is, I already dumped this in to my HMI here. So I was trying to remote into the HMI, but it didn't work out as planned. So instead what I'm going to do is I'm going to show you guys my screen or my camera just to show you guys what we have set up here. Hopefully you can hear me okay. So we have an H100 plus drive. We're running the 2-wire Modbus RTU connection, S plus, S minus, okay? And that's going to this HMI right here. And if we kind of look on the back, it's gonna be a little bit upside down, but the same S plus, S minus is going to COM3 in the back, just like the program told us it was doing. So this is actually, first page is showing you all the settings we need on the VFD. This is the wiring, actually just I showed you the physical wiring. So if we go to the second page right here, very simple. This is your run bit, so it's going to turn on your run. Let's see, oops, I got to go to auto. There we go. So let's stop it. Show it again. So I press the auto key on the drive. I could run. This is monitoring the run status. This is monitoring the run status. So this should be mapped to the same register, the same bit. If I stop it, it goes stop right here. Here's the DC bus. Remember, that's like the first register I recommend reading just to make sure you have communications with the device. I'm going to run it again. I'm going to let it ramp up. So we should see 55 hertz here. This one's going to accelerate to 55 hertz on the output. All right, so now we're matched. I can change my input. So this is a writing value. I'm just going to go to 45 hertz. Now it's starting to speed down to 45 hertz here. Okay. And then the last thing I'll show you guys is I mentioned all the parameters on the drives are mapped to registers. So here we have our Excel time. So I could change my Excel time to, let's do 5 seconds, decel time 5 seconds. And then now, if I'm going to go look on here, on the VFD, DRV3 and 4 is 5 seconds and 5 seconds. Try to get it without the glare. So we're actually writing all this over Modbus. So you don't even need to use the keypad as long as you map everything into an HMI or a PLC. We're also monitoring output voltage. We got a little gauge working right here. This is another parameter we could change. And I think it'll be locked out. Yeah, so we get a write mode error because I'm running. But if I stop it, I can change it now. I don't get any error. So just like you were programming stuff on the keypad, you can't change everything while you're running. You could change like XL, decel, PID stuff, some tuning things, but you can't change control stuff. So, all right, so troubleshooting. And some of this I kind of already mentioned, but we get reoccurring questions every day, is always make sure the polarity is okay. Plus to plus, minus to minus, okay? So S plus to S plus. If the polarity is wrong, no communications right away. Remember the best wiring practices, the 5 or 6 bullet points we mentioned. Also make sure that you turn on that termination resistor at the end of the line. Make sure that you have a unique ID number and a unique node address on each VFD. And we also recommend trying to read before writing, okay? So I'll open it up for questions. And also one other thing to mention is just how to get a hold of us. So we have our 800 number, 800-891-2941. You should be able to call us and we can help you out with Modbus. We can send you that table. We can help you with troubleshooting. And we also do have our shared inbox, which is techsupport.us@alliselectricamerica.com. Thanks guys for listening in. We appreciate it. If you have any questions or run into any issues, feel free to give us a call, shoot us an email. All right. Thank you. Have a good rest of the day. Thanks guys.